Just so you know, you're being recorded.
Yes.
I think maybe if you can go into full screen mode.
Yeah.
Perfect. All right, so if it's fine with you, we're going to get started. Marcos, is that okay? Sure. Okay, so our next speaker is Marcos Crichigno from Imperial College London, who will be talking about odd-dimensional Cardy-like formulas. So Marco, you have 30 plus 3 minutes, and then we'll have 10 minutes of questions. So go ahead.
Okay, thank you for the invitation to speak here. It's a wonderful conference. I'm amazed to see how many Latinos are involved in holography. So it's really great. All right, so I want to tell you about what I'm calling odd-dimensional Cardy formulas or Cardy-like formulas. They're very similar to the two-dimensional Cardy formula. And you'll see, hopefully I can explain where they come from and what the differences are. All right, so as all of you know, in this meeting, there's a very famous formula for two-dimensional CFTs called the Cardi Formula. And this formula tells you that if you look at a torus partition function, that is what is denoted here, with a modular parameter beta, and you take the limit of beta going to 0, then the partition function has its behavior. So it's divergent as beta goes to 0, and the coefficient in the numerator is the central charge, which characterizes the CFT. So this formula plays a crucial role in two-dimensional CFTs, in ADS-3 holography, and in the study of black holes, and so on. And I'm sure you're all familiar with this story. Now, the claim I want to make here is that for theories which are holographic, and in addition to conformal, they're supersymmetric. So that's what this SCFT means for, SuperConformal field theories. There's a certain regime analogous to the Cardi formula in which even in higher dimensions, you can write formulas which are Cardy-like. And here, there are the two cases that I'll discuss in detail, which hold in odd dimensions. So in 3D, you see that the geometry has a squashing parameter omega that squashes the two-dimensional sphere. Here I set the radius of the S1 to the unit, but you can always do that by changing the value of omega. And the claim is that it goes like 1 over omega, so this phi is just a simple function of omega, which I'll write soon. And the coefficient in front is not the central charge, because there's no such thing as a central charge in 3 dimensions, but rather is the free energy of the theory on the 3 sphere. Similarly, in 5 dimensions, now if you look at a S1 times S4 partition function, you have 2 squashing parameters for the S4 that have to do with the Cartan of SO5, rotating the S4. And you again get a Cardy-like formula where the coefficient now is the free energy on S5. And so these formulas are very easy and simple to remember. You can probably even memorize them. The coefficient is always I over pi. There's just a minus sign alternating between dimensions. So here, this phi is the, as I said before, is just a simple function of these omegas. And what I've denoted here, f of SD, is what you would call the free energy of the theory on the d-dimensional sphere. So these formulas kind of make sense if you had to guess something. If somebody told you there was a Cardy-like formula in higher dimensions, you would guess the free energy is what plays a role of the central charge. This is because it is known that the free energy in the sphere counts the number of degrees of freedom of the CFT, and this holds in all dimensions. So this was established in these papers, others. Now, what is more surprising is that at the same time is that this free energy on the D sphere is related to the partition function on the D-dimensional sphere. And therefore, these Cardi formulas are a relation between partition functions in different topologies. And that is a little surprising. But that already gives you a hint, in fact, that these formulas cannot be true for arbitrary regimes, but in particular, they require large n. So these are formulas which are not true at finite n and weakly coupled CFTs, but they emerge at large n as universal behaviors. Okay. So I should say that these are consistent with some previous studies of ABJM theory and cyber-like theories, and in the limit of omega being small, and it reproduces those results, but these are expected to hold at finite omega and require only large n. All right, so the goal of this talk is to explain to you why is it that we conjecture these formulas and what is the evidence that we have for them. So this comes from recent progress in understanding the microscopic origin of black hole entropy in asymptotically ADS space. Starting in 2015 with the work of Benini, Christoph, and Zaffaroni, who studied static magnetically charged black holes, and then various extensions of those black holes into other dimensions, and more recently into rotating black holes, so Kerr-Newman ADS. So this has been computed in, in many examples for various compactifications of string theory or M theory, type 2A, type 2E, M theory, massive type 2A. And for each case, there's always a different, well, there's a different boundary superconformal field theory in which you have to do the calculation depending on how you embedded your black hole. And the details differ a lot in each case. But the basic point that I want to make here is that, so in string theory, if you want to compute black hole entropy, you need to know what the black hole is made of. So you can count the microscopic objects that make the entropy. And you can make black holes in string theory in many different ways. So you can use the 3 brains, you can use the 4 brains, the 5 brains, and S5 brains, or M2 or M5 brains, and M theory, and so on. So what might look like the same black hole in 4 dimensions, once you uplift it into string or M theory, it is realized microscopically by different objects. In other words, if you open the hood, you'll see different things there. You have to count them differently. And the usual strategy for counting the entropy is that you choose the object that you want to study, say some Kerr-Newman ADS4, for example. Then you choose a microscopic model, meaning an embedding of this black hole into string or M theory. Then you know what the black hole is made of, for example, M2 brains. You identify the field theory, which is at the boundary. In this case, will be ABJM theory, for example. And then you count the states there in the boundary, and then you kind of take your result, and there's a method for pushing this all the way to the horizon. And once you reach the horizon, you obtain luckily the correct entropy.
Marcos, can I ask a question right there?
Yes.
Sorry, why is it necessary to embed it into string theory or M theory? Can't you do the calculation directly in the lower dimensional space?
What do you mean by this?
Because you said in the strategy there, you said you embed the solution into M theory. Or
yeah. So the point is that if you don't choose an uplift, if you don't commit to an uplift in string theory, then you don't know what the boundary field theory is, right? So it might be n = 4, or it may be as a deformation of n = 4, so n = 1 theory. And all these calculations come from a boundary field theory calculation. And if you don't know what the field theory is, then you can't do the calculation. that's
right. But once if you already know what the field theory is, then can you use the reduced theory in the bulk to compute whatever corrections you want to compute, or do you need to always work in the?
Well, so from the supergravity, well, you do know you do need the full embedding into string theory for the simple reason that you need to know what the Newton constant is, right? So how is the Newton constant quantized? So it's n squared if the boundary theory is n = 4. So for that only for that reason, you need to embed so you quantize things properly. And then on the field theory, you have to do the calculation of field theory. Yeah.
Right. Thanks.
Sure. Okay, so lots of details here, which I'm going to skip that I'm not telling you about, and people have figured this out in the last couple of years, starting from some work by Cabo Bisset and Bertilli and Sparks and collaborators, and myself and Leopoldo and a bunch of other people, that has to do with understanding the details of the supergravity setting more carefully. I'm not going to discuss any of that now, but just to say that there's some subtleties, and it took 20 years kind of to figure this out, since 1996, from the Strom and Jovlaffa up until asymptotically ADS black holes, it took a long time to figure these things out. And they're not terribly complicated, but they're a little bit subtle, and many aspects are not fully understood. But I'm going to focus in this talk purely on the field theory side. Okay, so as I said before, depending on the class of on the type of embedding that you choose, if you choose to embed your black hole into M theory or type 2A or type 2B, you're going to be counting different things. And you're going to do a very complicated calculation, but at the end of the day, you're going to get the area over 4 G Newton, where G Newton is properly quantized according to your embedding, as we just discussed. And the answer always comes out right. So this is very satisfying. You finally feel very powerful deriving the factor quarter, and it feels great. But you can play this kind of game ad infinitum, because there are infinitely many microscopic models of black holes and string theory, and it is ensured that you're always going to get the right answer. Right? So why is it ensured that you're always going to get the right answer? And the obvious answer to that is because string theory is a consistent theory of quantum gravity, and therefore you should recover the infrared physics that we know, okay? In particular, the Bekenstein-Hawking entropy. So it's great that Sturm and Javafa did it, and now we know how to do it in more contexts. But there's got to be a deeper reason why the calculations were out correctly from the point of view of these superconformal field theory calculations. Okay. How is it that the boundary SCFT always knows that a large N has to reorganize its degrees of freedom in such a way that it reproduces the Bekenstein-Hawking entropy of some dual black hole? So more precisely, the question I want to ask is, what is the universality property of holographic superconformal field theories that ensures that string theory has the correct infrared limit? And the answer I want to give is that it is precisely these Cardi formulas that I've discussed in the context of these rotating black holes. All right, so here comes a little warning. So the purpose of this talk is that by the end you hopefully remember these Cardi formulas, which are easy to memorize. But I want to give you a sense then how smart these superconformal field theories are and how non-trivial these Cardi formulas are. So if you set out to prove this Cardi formula as purely field theory, you'll see that it's a non-trivial task, and a lot of miraculous things happen. Calculations can be quite technical, but you should not lose sight of what is it that we're trying to do. Okay. So as I'll discuss, there are two main cases that I'll focus on, namely these 5-dimensional black holes. Now, in that case, the Cardi formula arises from methods of supersymmetric localization and studying some asymptotics of some special functions, particularly the Barnes multiple gamma function, whose asymptotics were just figured out in the year 2000. So that's kind of surprising. And some Bernoulli polynomials appear, and so on. Now, in the case of the 3D Cardi formula, so in the case of 5D, I'm going to be able to prove it rigorously for all 5-dimensional SCFTs with known gravity duals. For 3D, the evidence is more scattered, and we don't have a full proof, not even in a wide class of theories. But I'm going to show you in how it works in a particular class of theories, and you'll see that the flavor of the calculation is completely different. So this has to do with embedding the black hole into M theory using M5 branes. And the calculation you have to do is a calculation in complex Chern-Simons theory, which is not supersymmetric and has nothing to do with the purest calculation. So this is just to emphasize that no matter what you throw at the CFT, it's going to reorganize itself in a very smart way, so the Cardi formula is true, holds true. All right, with that warning, let's get started. So let's consider first type 2 model. So, but what I mean by this, I'm going to focus on 5-dimensional Cardi formula first. So I'm going to take a 5-dimensional Kerr-Newman ADS 6 black hole. Sorry, black holes is an asymptotic ADS 6. I'm going to uplift this to massive 2A or to type 2B theory. In both cases, they're realized by a collection either of D4, D8, and O8 planes and membranes, and in the type 2B case by PQ5 branes, bound states of NS5 and D5. But we can treat both cases all together at once. This approach. All right. So first, we need to decide what kind of so how to describe these 5-dimensional superconformal field theories with gravity duals. And as I just mentioned, these appear in the study of the D4, D8, O8 system in massive type 2A string theory. That's one class of examples. And the other one is these PQ5 branes. So here I give an example of how it works for this D4, D8, O8 system. So just like in N=4 super mills, if you want to figure out a new example for SCFT, you take a stack of branes. In the case of N=4, you take a stack of D3 branes. Now that is automatically conformal because there's no, the beta function vanishes for N=4 super mills. And you just back react that and you get your gravity dual. Now in 5 dimensions, the game is now so easy because if you take, say, for example, D4 branes, just pure D4 branes, and you take a near horizon limit, you're not going to get an ADS6 dual. And that has to do with the fact that 5-dimensional gauge theories, the gauge coupling constant in 5 dimensions is dimension full. So you don't actually expect to get, so the beta function doesn't vanish even classically. Okay, so what you can do is the following. So this is what Seiberg considered. He considered a setting of D4 branes together with some flavored D8 branes, an F of them, and an O8 plane. These are some technicalities are not terribly important, but that's a very particular gauge theory that lives on this world theory, which is given by this quiver. If that means anything to you, that's good. Otherwise, you can just ignore it. Okay, so the claim is that this theory per se is a gauge theory. It has dimensionful gauge coupling constant, so it's by itself not conformal. But Seiberg argued that it actually arises as some kind of infrared limit of some UV superconformal field theory. So even though this theory is not conformal, and in fact is not even renormalizable, what string theory tells you is that string theory kind of UV completes it into a finite SCFT in 5 dimensions. Okay? And these theories are not known directly. There's no Lagrangian description for these theories. Most of what is known about these theories is indirectly through this infrared description of them. But that will be sufficient for our purposes. So now we just imagine that we have this 5-dimensional SCFT, a Seiberg theory, I'm going to call it, on the boundary of this Kerr-Newman ADS6 black hole. And we want to compute the entropy of that black hole using the boundary theory. Now, the idea is that if the entropy of the black hole is computed by the partition function of the asymptotic theory, and this partition function of this UV theory is invariant in the RG. And because it's invariant in the RG, you can compute it in this infrared limit using this gauge theory description. So that is the strategy. Okay, compute the partition function of this gauge theory, and that should, in a certain limit, reproduce a black hole entropy. Okay, so luckily, people have been studying localization, in fact, supersymmetric localization methods in 5 dimensions. These are methods that allow you to compute the partition function exactly. So to all orders in perturbation theory, and also including non-perturbative effects. So they're kind of complicated beasts. They have to do with this story of Nekrasov partition function. And but I'm just going to describe it kind of in general terms. So in general, it takes a form like this. There's a contribution from the vector multiplet, there's a contribution from the hypermultiplet, and there's some integral over this variable u, which is a scalar in the vector multiplet. It's a real scalar in the vector multiplet of find the n=1 theories. Then you have to normalize by the dimension of the Weil group of the corresponding gauge group, and that the claim is that that is the full path integral. Okay. It just becomes a normal integral, although a very complicated one. And the details depend on what your phi manifold is. So the phi manifold that we want to take is the S4 times S1, because we're trying to compute this partition function, because the claim is that the Cardi formula, the Cardi formula is a formula for this partition function. And the claim of the Cardi formula is that it relates it to this 5-sphere partition function. Okay, that is the claim. So we want to compute these two things take a certain limit and see if they are related as predicted by Cardy. Okay, so to do that, one can consider a more general case first. It's convenient. So note that here I'm interested in the round 5-sphere, but I can consider squashed 5-sphere, which is given by this. So these are the 3 squashings. Then there's a certain way to see that this partition function can be on the squashed 5-sphere takes this form. So it's a product of 3 building blocks. These building blocks are the Nekrasov partition functions. If you massage them a little bit, you can bring it into this form where you have a prefactor and some complicated Bookhammer symbols here, which I'm not going to even bother writing down, but there's some explicit expression in terms of some infinite products that have to be regulated. So the important thing here is this prefactor, e to the psi, which one can show, just follow from some identities, is that it's given by these 2 Bernoulli polynomials, which are, it's a fancy term for just saying, well, there's some cubic polynomials, okay? And the claim is that in the large n limit, the partition function will be completely dominated by this prefactor, and so therefore by this cubic polynomial, B33, okay? So that's the S5 partition function. On the other hand, the S4 times S1 partition function takes a similar form, not identical. It comes from gluing 2 copies of Nekrasov partition functions on the north and the south pole of S4. It is again given by some ratio of Bookhammer symbols here on the right. And if you massage things appropriately, then you pick up a prefactor e to the psi. And the claim is that in the large n limit, this e to the psi dominates the partition function. Now this e to the psi, or e to the psi hat, is this ratio of Barnes' multiple gamma functions. So this is a generalization of the usual gamma function that has now two parameters. Okay, so the asymptotics of these functions were not known until 2000, but that's what we're going to use. So this is a good point just to contrast a little bit these 2 matrix models. So these 2 matrix integrals here. So all these variables x, they're like n by n matrices. So this expression and this expression are really different. So there's no reason to think that these 2 partition functions are related in a simple way, except that when you take the large n limit, because the prefactors become closely related. Okay, so if you carry out carefully the asymptotic analysis of those matrix models, you'll find that something quite remarkable happens, which is that the superconformal index, namely the partition function on the boundary of this theory, is the square of this squashed 5-sphere partition function with a particular map of these squashing parameters. So you take the S4, these are the 2 squashing parameters, and you map it in this way into the squashings of S5, and then you have this relation. So this relation is exact. There are no coefficients or anything that I've omitted. It's really the square. And then from here, it follows, in fact, directly by just a couple lines using homogeneity properties of the 5-sphere partition function, the Cardi formula, 5 dimensions. Okay, so basically just take the log on both sides, and then the claim is that if you have a squashed 5-sphere partition function, you can relate that to the round one, which is what appears here, just by pulling out some factors. So the dependence on the squashing just factorizes out like this. Okay. So this is a proof of the 5D Cardi formula for all theories which have known gravity duals. So this includes the Seiberg theories, orbitals of that, and also embeddings into type 2B string theory, and possibly more. So the conditions for this to hold are satisfied by all the theories that we know, but also by other theories that perhaps are also holographic and we haven't really studied in detail yet. Okay, so all I needed to prove this was a large N analysis of the matrix models. And a generalization of it to include deformations by mass parameters is also possible. Okay, so now let me discuss the M5 model. So the M5 model is the embedding of the ADS4 Kerr-Newman black hole into M theory sourced by M5 brains. So you could also choose an embedding where the black hole is sourced by M2 brains. and that would lead to ABGM living on the boundary. But if you choose an embedding which involves M5 branes, then the boundary theory is called class R, and it's a much more complicated set of theories. Okay. So as I just said, when the black hole is made out of wrapped M5 branes, of course you have to wrap them because you want to get a lower dimensional black hole. That's why we need to wrap them. They also have to be rotating because we want the black hole to be rotating. Now, and so the theory that lives on the boundary of this ADS4 black hole are these theories of class R, which arise from wrapping these 5 branes on 3 manifolds. Okay. And these theories have a name because they have no other known description. there's some guesses of what they may be, but in general, a general rule is that if a class of theories is given a name, it's because we can't really write down a Lagrangian for it. So they're known kind of indirectly. And I want to show you how to do the calculation of the entropy of the black hole in this context, and it will be very different from the previous one. So as I just said, you take your stack of M5 branes, you wrap them on a potato, and then you take that to be something that has very small size, and you obtain your 3D theories living on R3. Okay, and those are the theories living here on the boundary. Now, for every choice of M3, you can obtain a different theory here. So the theories that you obtain in the lower dimension are specified by a choice of a 3 manifold in which you can pactify. So, and they're denoted Tn of M3, and just denotes the rank or the number of M5 branes you had at the beginning. Now, these theories, as I said before, that they're suspected to be non-Lagrangian, just because the theory on M5 branes is not Lagrangian, and so the lower dimensional offspring is also expected not to be Lagrangian. But that's okay. For purposes of computing the index, I don't need to know the Lagrangian. There's another method. And this other method is the following. So consider, instead of wrapping the M5 branes, instead of wrapping only on a 3-dimensional manifold of this form, and then taking R3, consider replacing the R3 by a second compact manifold, B3. Okay. And now the claim is the following. You can wrap the M5 branes on this total 6-dimensional space, and now you can reduce in 2 different ways. You can take M3 going to 0, you can take B3 going to 0, and each one will lead to effectively to 3-dimensional theories which are different. Effective theories in 3 dimensions which are different. One of them comes from compactifying M3, and the other one comes by compactifying B3. But because they come from the same parent, the 3D correspondence developed by Dmowski, Gukov, and others conjecture that actually these 2 are intimately related. In fact, the partition functions are identical. That's the claim of the 3D correspondence. So if you're interested in computing the partition function of this class R theory on, for example, S2 times S1, which is what we need for the Cardi formula, you can do that by computing the partition function of a different theory on a different space. Okay, and this theory turns out to be this 3D complex Chern-Simons theory, okay, on the manifold M3. Okay, so the basic idea here is to use this correspondence to compute the index of this boundary class R theory by relating it to this Chern-Simons theory. So let me show you how this goes. So this is the thing we want to compute. This is what appears in the Cardi formula. By the 3D correspondence, this is related to the partition function of Chern-Simons theory on a hyperbolic space, sigma 3, which is denoted here. So H3 is a 3-dimensional hyperboloid, and you take a coset by a finite subgroup so to make it compact. And the partition function is just a standard partition function for Chern-Simons theory. Okay, so this is the Chern-Simons action, ADA. So the rotational parameter appearing on the left of the superconformal of the index appears here as an effective 1/h bar in this Chern-Simons theory. And the task, therefore, is to compute this partition function. So even though the theory is topological, the calculation is actually quite non-trivial. And so here we're going to adopt a strategy, which is the following. Because this is parameter omega here, let's take this parameter. Well, first of all, we analytically continue it to be I times omega, and then we take omega to be small. And so that means that that is equivalent to taking h bar to be small in some kind of Euclidean Chern-Simons theory. And so in this semi-classical limit, you can just expand your Chern-Simons partition function as a sum over all saddles. And saddles of the Chern-Simons functional are flat connections, because you have ADA, and with respect to A, you get dA equals 0. So you have to sum over all flat connections. And then you have to do a loop expansion around those flat connections. So that's what is running here. And it turns out that in order to test this Cardi formula, you have to go up to 2 loops. Okay, and all the coefficients have to come out exactly correct, so that everything combines into what is predicted by the Cardi formula. So one comment is that what appears here to be this effective h bar coupling constant is the rotational fugacity or chemical potential for the rotating black hole. And taking that to be small means the black hole is large. So this is the semi-classical expansion in the Chern-Simons theory corresponds to expanding around a large black hole. Okay, so I predicted that I was going to run out of time exactly in this slide, which I just did. But since I have extra 3 minutes, I'm going to use them, and I'm going to show you how this calculation goes. So you have to sum over all flat connections. And the claim is that they are a special class of flat connections which dominate that sum in the semi-classical limit. And they come from the following. So you take, remember that this Chern-Simons theory is on the hyperboloid. So what you can do is you can take your field bind and your spin connection, you can bind them into this connection omega plus IE. And that is a connection for SL2C, because SL2C is the symmetry group of H3. And then if you embed that into an n-dimensional representation of SU2, that gives you a connection of SL and C, which is what we're looking for. So not all flat connections of SL and C can be obtained in this way, but those which can are called geometric connections. And the claim is that they give either lower or upper bounds for all possible connections. So you've taken arbitrary connection A and alpha that is bounded above and below by this geometric or geometric bar that just amounts to choosing a different orientation. So therefore, if you're doing a semi-classical approximation, the expansion is dominated by this, the one which has the lowest action, which is this geometric bar connection. And so you have to plug that into your background and then make a 2-loop expansion around that geometry, and cross your fingers that the coefficients will come out right. And so luckily for us, this was done for related but different reasons by a number of different people, including some mathematicians, but also some physicists studying holography, where you can just, this is a trivial calculation because it's a classical piece, anyone can do that. The 1-loop calculation is actually quite complicated, and mathematicians have derived this. And the 2-loop calculation, there's no direct calculation of it, but it can be inferred by using other properties of holography. And if you assume that that is correct, then these coefficients are 6, 1, 6, and 1 over 24 exactly combine, so that when you put everything together into this expression here, and you take the logarithm on both sides, and you use a 3D correspondence, the function that you get is exactly which is predicted by the Cardi formula, the 3D Cardi formula. So here I use the fact that the free energy on S3 for these theories of class R is given by this. Okay, so you find a perfect match, and that is very strong evidence for this Cardi formula 3D. Okay, so let me just quickly summarize. So as I said at the beginning, if you got lost and derailed, you went off the cliff together with the car with all the technical details, that's fine. I just hope that you remember that the main conceptual point. And the main conceptual point is that black holes can be realized microscopically by different objects in string and M theory. They can be different brains in different dimensions, or membranes in string or M theory. no matter how you realize these black holes, if you calculate the entropy, you should get the Begues-Hawking entropy. And what ensures that is, in the case of black holes in ADS4 and ADS6, rotating black holes in ADS4 and ADS6, is this Cardi formula, which can be written like this, for a generic dimension. Okay, so what we did is we could prove this Cardi formula for all 5D theories with ADS6 duals, and I gave you evidence, strong evidence for it to be valid in 3D, but still kind of, complete proof in 3D remains a little elusive up until now. So a couple open questions would be, natural question is whether if any of this holds outside of supersymmetry. You may think that maybe that could be the case because this free energy counts degrees of freedom of field theories, even non-supersymmetric ones. So we don't know. Another question you might ask if there's a way to prove this, which is just exploiting just like in 2 dimensions, you can prove the Cardi formula using modularity. Is it possible to prove this formula using some kind of notion of modularity or something analogous to it in higher dimensions? Finally, a question which arises in 3D is whether you need to take large N and also this semi-classical Cardi limit or omega is going to 0 or not. And this relates to a question on whether there could be phase transition as the black hole is very large. So there the Cardi formula holds, but as you shrink it down, could it be that it breaks down into multi-center solutions and the Cardi formula breaks at that point? All right, I'll stop there. Thank you.
All right, thank you very much, Marcos. That was very, very interesting, at least for me, and I know for a few more people in the audience. So Leo raised his hand. Leo, go ahead.